basically, when we talk about calculations, two things you need to do, well, a few things you need to do. You need to go from grams of magnesium to moles of magnesium, and grams of oxygen to moles of oxygen. We're going to talk today how you do that. I think that's kind of it. And some of you maybe had gone off to bigger and better things, but what I said at the end of lecture, what I said at the end of lab yesterday, I've done this before, since it's helpful for you when you come to take your test, your unit exams, to have your calculations knocked out for your lab, because sometimes they like go hand in hand. If you turn in your complete calculations and your data, your copy of your lab data, you don't, when you come to take your test, if you have it in hand, when you come to take your test next Thursday, then you don't have to do the other part, the summary. Oh yeah. So that will be the pattern this semester.
So like calculations.
The calculations, and when you do your calculations, you have to make sure it's labeled and everything, but yes.
So like the really just given this paper with my
Yes, ma'am. As long as you label your calculations, yeah. And I heard some people are like, oh, I'm just gonna go ahead and knock that out. Okay, so I'm excited. You're excited. We're all excited. So let's see what we need to know about this topic. Okay. So a lot of you guys are already familiar with the concept of a mole. If you're not, we're going to kind of hit it. But we need the concept of a mole actually to count particles, and then we'll talk about what how molar mass fits in. So I have a little video here to show you. It's another TED Talk on the definition of a mole. I feel like I'm kind of talking over kind of the sound out there, but anyway. I think I said this before, we pick on one isotopic form of carbon. Carbon 12 has a mass number of 12, and if you have 12 grams of carbon 12, then you have a mole of carbon 12 atoms. So this is the magnitude of a mole. So I said a mole is counting particles. This actually, there isn't some uncertainty in this number. This is not exact. So a mole is equal to approximately, with 4 sig figs in its coefficient, 6.022 times 10 raised to the 23rd power. Sometimes with students I write that on the board here, but I think you guys are okay. You can picture taking this decimal place and moving it over 23 places. That's a big number. And I'm going to kind of watch this TED Talk, we got time, to kind of show you how big that number is. We have an equivalency statements like you see up here. It uses conversion factor. So we're going to actually kind of take a mole and see how many particles they are, usually like atoms or molecules. And similarly, we can pack up a certain number of molecules or particles into how many moles that is, using that as equivalency statement. But before we get there, with regard to rice particles are pretty small. If we, based upon the volume of a rice particle, if we had a mole of rice grains, it would cover all the land area of the world, up to 75 meters. But actually, that's problematic because as much a staple as rice is, a mole of rice grains have not been grown since humans have been cultivating rice to grow and eat it. Mole of rice grains would also be problematic because if you gathered it all into one bundle, a box would have to be 120 miles on each side to contain your mole of rice particles. I always think of the Stay Puft marshmallow guy for this one. Mole of marshmallows is not a good thing either. It covers the United States up to a depth of 600 miles. Mole of snowflakes covers the U.S. up to a depth of 2/3 of a mile. If you were going to count, like, 1001, 1002, 1003, okay, and we were going to count up to a mole's worth of kind of clicks like that, it would take everybody on Earth, specifically though, we'd have to have everybody on Earth, and we'd have to have 51,000 Earths full of people counting that like that for 75 years. So that's just a lot, okay? So if you've ever taken any programming, and I've taken just a little bit way back when, but one of the things they do with your programming is you take your computer and make it go into a loop. So if you were to have, and this is a fast computer, go ahead and loop it to count a 1 mole's worth of iterations. The same computer, by the way, is so fast that it could go through that many iterations of the number of people in the United States at the time it's written in less than a second. But that same computer would take about 1.9 million years to count Avogadro's number. So it's just a big number. Hockey pucks, not a good thing. It'd be equal mass to the moon. Basketballs, we saw that in the video, would be about the size of the Earth. So don't go for the mole thing. And for this one, I always think of like that I Dream of Jeannie, where wasn't Roger, it was the other guy who actually kind of owned the genie. He could ask for anything and Jeannie would make it appear. Well, if this guy asked for a mole of pennies, that would be bad. Because it would be bad. But a mole of pennies, if everybody had a mole of pennies, here, this is how bad it would be. It would cover the land area up to a depth of 420 meters. But that's a lot of money. If you just take the decimal place and move it over 2 places from the right back to the left, that's how many dollars that is. And it's kind of like the video said, you have a lot of money. So instead of rice grains or hockey pucks or basketballs or pennies, of course, the concept of the mole is very helpful in chemistry because of very small things, atoms and molecules. So that was all kind of simple. Here's a figure from your OpenStax textbook. That little droplet of water contains about 100 billion times more than the people on Earth. So molecules of water are very small. All right. So here we have this equivalency statement, and notice now I've gone ahead and said a mole of atoms is equal to 6.022 times 10 to the 23rd atoms. This equivalency statement, as we've talked before, you can knock out two conversion factors. Any equivalency statement, we can put, in this case, moles over atoms, 1 mole over 6.022 times 10 to the 23rd atoms. We can also say 6.022 times 10 to the 23rd atoms over 1 mole. Okay. Notice that actually, grab my pen here. As we get going, I don't know how to say this. I guess I would. I was going to say the thing in brackets, I'm not sure I would necessarily say that. It starts with the letter, maybe I would. Starts with the letter I. What's the relationship between these two? I use the word flip, but how are they related mathematically? They are the inverse of each other, exactly. So we've kind of come back to something that we've been working with. So no whiteboards yet, but they're coming, don't worry. We're going to work 2 problems using those 2 ratios. For the first problem, we're going to go from the number of atoms to moles. The second problem, we're going to go from moles to number of atoms. Now, in this case, you see some words in brackets, square brackets. Those square brackets may or may not be listed in the problem that you get to work like this. So in other words, for problem number 1, it's just might say how many moles is 1 trillion hydrogen atoms? How many atoms is 0.55 moles? Okay. All right, so the first term is going to be, for the 1 trillion hydrogen atoms, we're going to assume like exact, there's no uncertainty in that. So 1 trillion is 1 times 10 to the 12. So if I go back a few slides, you saw, excuse me, the ratios of taking that equivalency statement, we get the 2 conversion factors. How many people think I'm going to use the first conversion factor listed right here? How many people think I'm going to use this one? How many people think I'm going to use the second conversion factor? I'm going to use the first conversion factor because I want atoms to cancel, and I'm going to be left with moles. Okay, so it looks like this. Okay, so my first term over 1 is 1 trillion hydrogen atoms. My second term is going to be the ratio 1 mole of hydrogen. Notice I didn't put 1 mole of hydrogen atoms, I just put 1 mole of hydrogen over 6.022 times 10 to the 23rd. Get your fingers ready. If that 10 to the 12th is exact, how many sig figs do I need to round this to? 14 sig figs. I'm liking 4. I'm liking 4 sig figs, yeah, because I'm going exact with that. Yep.
I don't get how you get like the whole 10 to the 12. That's the part.
This one, this 10 to the 12th, or the.
But yes. Did you just put it in the calculator?
I just put it in the calculator.
Okay.
I can't do that in my head.
Okay, yeah.
Yeah, so in this case, you just take, I would say 1 times 10 to the 12th divided by 6.022 times 10 to the 23rd. And you get an idea of what the magnitude of the exponent of 10 will be, as you may kind of remember. If you just take the 12 minus 23, that kind of gives you ballpark what the exponent of 10 is going to be. Negative 12. Okay, next one. So in this case, we were going from 0.55 moles. Notice I didn't say of atoms, but 0.55 moles. I put that over 1, and now I'm going to have the inverse of this term. 6.022 times 10 to the 23rd atoms over 1 mole. Get your fingers ready. How many sig figs? Fingers or just shout. You guys are.
3.
Why is it 3? Yeah.
Oh, yeah.
It's just 3.
Yep.
That's a little like, what? No. Because sometimes I get in a hurry. So yeah, it's just going to be 3. Yeah, that one doesn't count. All right, so here we go. You plug it into your calculator. It's like magic. 3.34 times 10 to the 23rd atoms. So when working problems, science problems, you should kind of take a last look at it and say, does that seem reasonable? Well, if I have, 0.555, that's about a half a mole. And it seems like if I have a half a mole, I should have about a half of 6.022 times 10 to the 23rd, and 3.34 times 10 to the 23rd is about a half. Okay, so it never hurts to kind of look one last time at it. If I have up here, this first problem we worked, if I have a trillion, which is 1 times 10 to the 12th atoms, you're like, dude, that's so not close to a mole, okay? That's not a mole yet. So I know I should be looking for a small number. So that is a small number. Okay. The reason I'm not doing whiteboards is because actually I want to emphasize one problem, and actually at the end of this set of lecture slides, we're going to do a problem that reintroduces this concept. All right. So that's all I'm going to do for that. Now, kind of switching gears. I feel like we're switching gears. We talked about, the definition of a mole. A mole is 6.022 times 10 to the 23rd. Anything. Usually small things. So molar mass, I like it in science when the word actually is very descriptive. The phrase molar mass means the mass of 1 mole. That's it. I think I said, what did we say, hockey pucks. Let's see, if you had a mole hockey pucks, that would be equal in mass to, the moon maybe? So the molar mass of hockey pucks is the moon. You just got to get a mole of those things together. Okay, that's what molar mass is. That's wonderful. But it's in not in hockey pucks. Molar mass is in grams to get 1 mole of those things. Okay? So molar mass, the units are grams per mole. This is a really important concept, a really important thing that will be used throughout this class, the concept of molar mass. We said that if you know the units of anything, like the molar mass is grams per mole, we can look at the units and it gives us a clue how we can use it to get between units. So molar mass is awesome to go back and forth between grams and moles. Just like density is awesome to go back and forth between grams and milliliters. All right. So how do we get to the molar mass of things? Well, we're going to start with the molar mass of each little element. It's wonderful. So the molar mass for all the elements is numerically equivalent to something we've already talked about, the average atomic weight. What are the units of average atomic weight? AMUs. Yeah, units of how much an atom weighs, an average atomic weight, are AMUs. Units of molar mass are grams per mole. But I mean, I could go up here and I could just pick up an element, silver, that 107.8682, that's AMUs for how much a silver atom weighs. And that's also grams I need to get set aside in order to have 1 mole of silver atoms. It's its molar mass. Okay? Bless you. The molar mass of silver is 107.8682 grams per mole.
Molar mass.
Molar mass is the grams per 1 mole. Yeah, molar mass is the grams per 1 mole. Exactly. Yep.
So could we just say 1 AMU equals 1 mole, or is that not?
Well, actually, how did we do that? We said that, and I'm going to show you kind of a proof here. No, you can't say that. How did you say it?
1 AMU equals 1 mole?
Nope.
The AMUs are different on each.
Yeah, we did, and I'm going to kind of actually, how did that work? I know, 1 gram is equal to 6.022 times 10 to the 23rd AMUs.
Okay.
Okay, so no, but yes. And actually, AMUs is mass, and mole is counted particles. So that wouldn't work.
Okay.
So, but I think you're on something.
And it's more important because MUs are not grams.
AMUs, grams are mass, and AMUs are mass. Okay, so this works. Okay, but this doesn't work. Yeah, and if we go back to the silver thing, we said 1 mole of silver is equal to 107 point, what did we say, 6 or 8262 or something. 262 grams. So actually, kind of back to maybe what Stephen was saying is we definitely we do molar mass is our link kind of between mass and kind of particles, but it's different. We can't just say it general. We have to say it specifically.
Okay.
Yep. Okay, cool. So, I don't know why it gives me that dirty look. Okay, so again, those decimal numbers do double duty. And I like to kind of apologize, but that's not a random, there's a link between that, for that being the case. They do double duty. They're the average atomic weight and also the molar mass for the elements. Okay, and so here's my little kind of proof. I'm picking on copper. I could pick on any element to do this. But I'm going to kind of show you how this works. So we can go to the periodic table, and for copper, the decimal number is 63.55. That's AMUs per 1 atom of copper, because each atom weighs something different. I can introduce my next term, this one up here that I said. Okay, I said with regard to mass, 1 gram is approximately equal to 6.022 times 10 to the 23rd AMUs. That's all I'm doing. I'm kind of introducing, and the reason I'm doing is introducing it that way is because I want units of AMUs to cancel. Now I have grams per atom. My last term actually is going to be the definition of a mole. We know that 1 mole of atoms will be 6.022 times 10 to the 23rd atoms. Now the reason I've set these 3 terms up this way is when I let units cancel, units of AMUs cancel, okay, units of atoms cancel, and what units do I have left? Grams per mole. And I don't have to get my calculator out for this one. Why? Yep, these 2 quantities, Avogadro's number, cancel out. And so quite simply, I have 63.55 grams per 1 mole. And again, we could do that for any element. I just picked copper. It's just kind of a little proof. And I'm showing you how that works. Okay, so I have some pictures here to kind of show you quantities. And of course, density is an issue, not to mention the nuclei. We've been talking about how atoms of different elements are different. The nuclei of the atoms differ by the number of protons that are in them. So they're going to have different masses and all that. But what somebody's done is taken zinc, copper, magnesium, zinc, carbon, magnesium, copper, sulfur, silicon, lead, and tin. Yeah. And has 1 mole of those atoms. And so you can see the grams then, those grams, are we on the same page? Those grams would be equal to what you see on the periodic table. Just trying to make a point here. Similarly, we have copper. This is copper, this is liquid mercury, this is solid sulfur, and in the balloon is helium, so the same thing. Molar quantities, molar masses. Same thing here, okay? All right. So molar mass, we're going to do a lot of these calculations for various reasons. Here, I'll let you guys take it. I finally have a little thing to 10 in there. Yeah, this calculation is here to stay. So let's work a problem. And again, the thing in brackets, when we get going, probably will not be there. Okay. So we're going to work a problem here. This would be what and I'm bad about not reading the problem, just doing looking at the units. This looks like a grams to moles problem. Okay, just looking at the units, grams to moles. So how many moles is 0.487 grams of calcium? Remember on your test on Thursday, you're definitely going to have that periodic table. I'll give you a fresh copy of that black and white periodic table without the names. Okay. So in order to work this problem, we need to use the periodic table to look up calcium and look up the decimal number for calcium. You're going to find it's 40.08 grams per mole. Now, I've been saying that you really can't, and I really shouldn't see it in you guys. I see it in some of my other science students, but you should never work a problem 40.08 G/MOL. It shouldn't be your unit shouldn't be like that. You should unpack it. So you know what I'm going to do. I unpack it or fluff it out. What that 40.08 grams per mole means is there's 40.08 grams approximately of calcium in exactly 1 mole of calcium. The inverse is also true. So there we have our 2 options for using molar mass to work this problem. We can also flatten it out. Okay. So I'll get you started. Oh, by the way, I'll get you started. So the first term is going to be 0.487 grams calcium. Put it over 1. And then go ahead and I'm liking what I'm seeing. Go ahead and write the next term. It's going to be one of those 2 ratios we had on the previous slide. You just got to be unique. That was just a good idea. For calcium, we said it's 40.7 grams per mole. So, we rounded to 2 decimals. How you like? simply, it's which is that 487 grams. Well, if you want to, but see, this is what you do that. 87 grams over 1. Notice my grams are going to
So we can do this.
Yes. Did everybody get acquainted?
I did after I got with one of those. Christian, that one too.
Yeah, I'm thinking my slide might be wrong.
There's no point. If you round them, it should be a 2. It should be a 2. Oh, wait.
Yeah, I'm thinking. So you think it should be 2?
Oh, yeah, 2, 2.
Yep. Good job. I think if I remember. Yeah. Is that better?
Yeah, it's better than
So one of the things I've been telling you about this Alta homework, as problems get more interesting / difficult, I really would have a notebook handy next to my Alta, where I was working Alta problems, and I would write out the stuff. Alta, one of the reasons I chose this to go this route, maybe over other vendors, is it's really good with showing you. If you get it wrong, it will show you. And it uses it. Whoever set up Alta, the chemist behind the scenes, they use factor label. Okay, it's not just Mrs. Snipes using some crazy thing.
I gave you another attempt. I realized that on some homes I give you another attempt.
Another attempt?
You have to actually enter a number, yeah.
Okay. So let's work another one. And again, I just focus on units. To me, this looks like a moles to grams problem. Moles to grams problem. You buy that? Just looking at the units. I have moles and question mark mass. So moles to grams. So again, the thing in brackets probably won't be there. I'll simply say what mass in grams is 1.33 moles of boron. So you know what we're going to do. We're going to use the periodic table as our friend. We're going to look up boron. And the decimal number for boron is 10.81. And that would be AMUs, how much of weighted average of boron is, 1 atom. And that would also be its molar mass. Okay, so those are these two ratios are our options. Let's see what y'all do with this one. I'll get you started. You're going to put 1.33 moles boron over 1. Notice if I'm working this problem, there's only one element like this, I might just put 1 mole over 1. 1 mole B, 1 mole boron over 1. Now we need units of moles to cancel. We'll be left with units of grams. So, what would we say? 10.81 grams per mole. Yep. Are we good with that? And I mean, it seems so basic. And it's like riding a bike. The more you do it, the more it'll like sink in and stuff. But
Oh, yeah, but I know.
oh yeah, that's weird. But I'm now seeing your picture. Okay. Yay. Okay. So the coup de grace. One more problem, people, and it's going to link molar mass. The element we're going to pick up is lead. It's going to link it's going to use both molar mass tools and Avogadro's number. Part of the problem, and it's something that hopefully you'll get some experience doing. Oh, by the way, I didn't bring my little sheet in, but remember I gave a sheet out Wednesday of problems that are going to be due Monday related to this. And hopefully you guys are kind of knowing now how you can finish your calculations for the lab you did yesterday. You have to knock out the moles of magnesium using magnesium's molar mass. I love that phrase. And moles of oxygen using the mass of oxygen's molar mass. So we're going to pick on lead. What I started saying is it's hard to know when to use Avogadro's number or not. And just doing problems will hopefully get you down the road. You use Avogadro's number when you know counted particles or you're trying to get to counted particles. Usually don't use Avogadro's number if you're just going between moles and grams. So here we have a lead sample. The mass of the lead sample is given, and we're supposed to knock out the total number of lead atoms. Okay? So I think I am. See, did I? Oh yeah, I kind of showed you what I would do. I would start from left to right. I would go from the mass of lead to the moles of lead, using lead's molar mass from the periodic table. By the way, lead just kind of, it's one of those ones that when you go to get its decimal number, it only has one decimal, which I've looked this up before, and I think it has to do with it's hard to pin down and get a really solid average atomic weight on it because it's hard to get isotopic abundances. Anyway, we can go from moles of lead to number of lead particles using 1 mole is equal to 6.022 times 10 to the 23rd atoms. So work that problem. What's your first term going to be? For most of us.
0.330 grams.
Yep, 0.330 grams over 1. And again, I kind of said this before, since I'm only dealing with one element, a lot of times I wouldn't put the lead, the PB, but you can. That's right. And then
Is this a 3-step one?
Mm-hmm. Like our PB atoms, like batons. So, those boron atoms are batons.
Because she does just one mole is like.
It's like bouncing your checkbook. You get 2 that match.
Yeah, you're right.
Okay, I would have.
So that's not something's not quite. And you need units or you're not gonna get the credit on the test.
So, like, how we did it in previous chemistry, like, it was just 6 points. Like, so do we get, if we do that?
Just how this, that gives us, as you know, the round. So I have this what would probably be the same, because you can't justify, I have this one. Gives me no choice.
I don't, and it's because I'll start using units and then I'll forget to write them down, and then I'll forget to cancel them out. So the test is not going to go well for Madison. See, I forget to use them. Is there some truth?
That's not what they got back there. So this is
I mean, you, like,
I ended up with it. So, don't ask to do it. I start with them, and then I lose them, and then I find them again. Because for me, when I do my math, I'd rather write it out and then use label than write it later.
And plus, okay, if you're throwing this out, when this goes out, so what, there's 3 terms. What if you had 7 terms?
7, it's gonna be 2 where they cancel, so you have to have then line up where they cancel.
I'm just saying, it gets harder to.
The more labels you have, the harder you have.
It's messy when they go out the end. I'm the same way as her. I don't like labels, and I would just write down the numbers and
Yeah.
labels.
In other classes, you might could, but not this one. I will be so sad on your test on grade it. Nice app. Oh, love it. Okay, I still need to. I'll have to get my extra credit points on there.
I have
Okay,
two
so
of them. Is there a difference? This
minus this divided by this. So I just focus on
one of
numbers
them
that
will
are
tell me
equal.
density, and the other one won't.
Yes.
The other one just gives me, like, when they were created and the Wikipedia stuff.
Well, it's a little anticlimactic, but once you have that and you're satisfied, we're done. That was the last problem. So this, like I said, I think there might be an Alta. Do the Alta, but the Alta's not much. If there is anything out there. You really also, I gave you.
You gave us, like, the worksheet.
Yeah, just the back page. Oh, and one more thing, don't forget, I already said it, but I really would work those problems at the end of the unit. I don't think, I'll put it this way, in my 16, 17 years teaching this, I have not had a student who worked those and bombed the test. Never ever. You work those, and that will actually set you up good for the test.
What problems?
The problems in your lecture, like
At the very end of this unit, and there's like this section here.
But also, don't forget I do definitions and such too.
Yes,
So,
I'm making flashcards for her.
okay, good.
So when we try and get